Good afternoon, everybody, and welcome to this Purdue Engineering Distinguished Lecture Series. For those of you who do not know me, I'm Rao S. Govindaraju, and I'm the head of the Lyle School of Civil and Construction Engineering. So this distinguished series began in about 2018, with the idea being to invite world-renowned faculty and professionals to Purdue Engineering to encourage thought-provoking conversations and ideas with faculty, students, and others regarding grand challenges and opportunities in their fields. So besides presenting a lecture to a broad audience of faculty, graduate, and undergraduate students, the speakers engage in an interactive panel with Purdue faculty and students. So today we have Jerome F. Hajar, Jerry Hajar, who's a CDM Smith Professor, University Distinguished Professor, and Department Chair, Department of Civil and Environmental Engineering at Northeastern University. Jerry is also Director of the Laboratory of Structural Testing of Resilient and Sustainable Systems, aptly acronymed STRESS. Okay. He has served as the Chair of the Structures Faculty and Deputy Director of the Mid-America Earthquake Center at the University of Illinois at Urbana-Champaign, was a faculty member at the University of Minnesota, and was a structural engineer and associate at Skidmore, Owings, and Merrill. His research and teaching interests include analysis, experimental testing, design of steel and composite steel concrete building and bridge structures, regional modeling and assessment of infrastructure systems, and earthquake engineering. He has published over 300 papers, edited 5 books on these topics. Jerry also serves on the American Institute of Steel Construction, AISC committees on specifications and several of its task committees, including chairing Task Committee 5 on composite design and the AISC Sustainability Committee. He is the president of the American Society of Civil Engineers Structural Engineering Institute and has served on the SEI Board of Governors and several other ASCE and SEI committees, including serving as a past chair of the ASC Department Heads Coordinating Council and as the ASC Minnesota Section President. Jerry was elected as a member of the National Academy of Engineering in 2022, was made a fellow of ASC in 2007 and of SEI in 2013. He was awarded the 2024 Structural Stability Research Council Lynn S. Beadle Award for Lifetime Achievement, the 2024 and the 2004 AISC Special Achievement Awards, 2023 ASC Thomas L. Lennox Excellence in Civil Engineering Education Award, the 2021 AISC Lifetime Achievement Award, the 2016 ASCE MOSIF Award, the 2010 Popular Mechanics Breakthrough Award, 2009 ASCE Shortridge Hardesty Award, the 2005 ASC T.R. Higgins Lectureship Award, the 2003 ASC Walter L. Huber Civil Engineering Research Prize, and the 2000 ASC Norman Medal for all his research work. I'm not sure this was the entire list. It is very impressive. Did I also mention he's a department head? Okay. Jerry is a registered professional engineer in Illinois and Minnesota. So with that, Jerry, it's all yours.
Yes, thanks so much. Yeah. Okay, good afternoon, everybody. GS, thanks so much for reading all that. Thanks to you and Amit Varma for the invitation. Really great to be here at Purdue. Great to be seeing and working with the department today and with the college. So I'm going to talk today about work I've been doing for probably over 2 decades at this point, leading towards looking at new solutions for sustainability and resilience in the built environment. I am a structural engineer, civil engineer, so we'll be talking predominantly about structural engineering today, but we'll be thinking about a few broad themes. And it's certainly a great time, in my opinion, to be an engineer, to be a civil and environmental engineer. It's a time when we are increasingly thinking globally. In so many ways, what happens globally is influencing our work here, We're developing new design strategies from our learning from our friends overseas. We're thinking increasingly about supply chains and how they impact our profession. It's a time when we're thinking increasingly holistically about complex urban regions. And a number of communities around the country, around the world, are starting to do things like commit to carbon neutrality, to think about net zero economies, and certainly I'll be talking today about how that impacts civil and environmental engineering. It's a time when the power of networks continues to grow and expand and impact our profession, certainly networks of civil infrastructure, but also networks of people. And from what I'm seeing, some of the historical organizations and professional institutions that really underpin our profession are having to evolve quite aggressively. And new types of organizations, networks of people, are starting to be formed that are providing some pretty interesting opportunities. It's a time when the kinds of decisions that we make as civil and environmental engineers that impact the social fabric of our communities are increasingly and rightly being questioned. And where we're having to think about new ways of integrating with communities to evolve our decision making in our projects to be much more appropriate for the kinds of societies that we're trying to help build. It's a time when we have new design procedures, new materials, new systems, a lot of innovation going on in our profession. We have about 60% of the world's population living in fragile coastal regions. And I think we're seeing quite directly how that's impacting our communities. And as a structural engineer, I think it's particularly interesting how much we're starting to talk directly about the environment and about environmental engineering and integrating these so that environment is very much driving decisions that we make in civil structural engineering. And there's lots of different initiatives going on that are trying to pull a lot of this together. For example, the American Society of Civil Engineers started what they call the Future World Vision about 5 years ago. Jerry Buckwalter, their chief strategy officer, was leading this. And Jerry says change is coming. And it's on a scale that can drive confusion and dysfunction unless industries, organizations, and individuals are prepared to tackle new realities. And he shows some examples here of some of the things happening in our world that are going to have pretty dramatic impact, certainly impact on our profession, impact on our communities. And so they were trying to get organized by thinking about 5 innovative types of cities as examples of how to pull together and study the influence of new technologies on civil and environmental engineering. And you could see a whole range of technologies here. This is an exercise in gathering information, providing information to the civil and environmental engineering community, but just getting us to think about this in a much more direct and holistic way, I think is important, and this is an example of one initiative. But as I think about all these, for me, the biggest driving problem is shown in this slide. And this is from Arun Majumdar, the Dean of the Dorr School of Sustainability at Stanford University. And he is showing here how the population of the world has grown over a very long time span. And you can almost think about this growth, and just in my lifetime, the population of the world has more than doubled. This is like a delta function. This is like a spike on the planet. And we have to ask ourselves, why would we assume that the planet can handle this without us really thinking aggressively about how to address it? And so that gets me thinking, what can we do in engineering to address this? Dr. Majumdar calls this the human tsunami. And this has led to the human consumption tsunami, the energy consumption tsunami, and therefore the global CO2 tsunami. And so as an engineer, I ask myself, how do I help address this situation? And indeed, civil and environmental engineering is right at the eye of the storm of creating the issues, and therefore right at the eye of the storm of creating the solutions. And I'd be advocating that we need to be right out there, out front, leading on these topics. Why? Well, construction and use of buildings takes about 40% of all energy use. About 40% of all material flow is in construction and use of buildings. About 40% of all waste production, about 40% of all greenhouse gas emissions, another 30% coming from the transportation sector, another 30% coming from industrial engineering, industrial facilities. So civil and environmental engineering, mechanical engineering, electrical engineering, all types of engineering playing into a lot of this. And the governments around the world have figured this out. You might have picked up last December, the United Nations held their climate change conference. They call it the Conference of Parties, 28 in this case, so COP28. It occurred in Dubai. And as part of this, there were many thousands there, and they do a whole range of things. But one of the things, that they do is create what they call the breakthrough agenda, or evolve their breakthrough agenda. The breakthrough agenda is the countries getting organized to determine how best to accelerate innovation in different sectors of our economy, specifically to drive solutions for climate change. And for some time, they've had 5 sectors that they've been looking at: steel, hydrogen, agriculture, power, and road transport. And then at COP28, they added 2 new sectors: buildings and cement and concrete. And so as civil engineers, steel, buildings, cement and concrete, right up the middle of what we think about as structural engineers. And you can see the countries listed here that are attempting to lead this effort around the world and what some of their goals are. And indeed, countries are starting to evolve their commitments to what they can call net zero emissions economies. So Europe has been a leader on this. The EU has committed to 2050. The US has now committed to 2050. China, 2060. India, 2070. And we'll see if we can get this done. I mean, this is hard. But at least we've gotten a bit organized at a governmental level. And it's going to be the engineers that are going to be so critical to the solutions. And of course, we see what very likely is the impact of this already. For example, in the hurricanes that are happening around the world. And in the structural engineering profession, for several decades now, we've had a term called disproportionate collapse of a structure. It started with a collapse, many people say, in 1968 in the UK, where a structure collapsed disproportionately to the size of the load. The load was relatively small, shouldn't have created a collapse. Really kind of a dormant term, though, in our world until 9/11. And these, of course, many engineers would say these were not disproportionate collapses. The loads and the fires were huge. But it got the community talking about disproportionate collapse. A lot of work went on, a lot of analysis work, design work, many people working on disproportionate collapse since then. I've been starting to talk about disproportionate collapse of regions as something that we need to integrate into our individual projects. And you could see many examples of this. Hurricane Katrina, probably one of the clearest ones, where the levee breaks wiped out huge regions of New Orleans, and those regions really still haven't come back to the way they were as fully. Other examples, the tsunami that occurred 2011 in Japan, taking out the Fukushima nuclear power plant. That region still struggling to come back from this major event because one structure got significantly damaged. And so today I'm going to be talking about sustainability and resilience. And sustainability, defining it as, for my purpose, dramatically decreasing the material use, greenhouse gas emissions, pollution, and waste in civil engineering, structural engineering. Resilience, bouncing back quickly after extreme events. And showing here some of the publications coming out of the Structural Engineering Institute and American Society of Civil Engineers and the federal government that are really starting to look at these much more directly. So my own thinking on a lot of this started when I was a young faculty member. because of the 1994 Northridge, California earthquake that occurred January 17th, magnitude 6.7 on the high side of a moderate earthquake. So not the big one by any means. But at the time, it was the costliest natural disaster in the country's history. And one of the reasons why was that relatively new steel building structures, steel frame structures, we call them moment-resisting frames, fractured, many would say unexpectedly, at the intersection of the steel girders with the steel columns. That region had fractures in it that required major repairs. And in fact, Southern California, where this occurred, basically shut down steel construction for a couple of years while we tried to figure out what happened and how to prevent it from happening again. And if you shut down steel construction in a region, that's going to decimate the economy, and it became the costliest natural disaster in the country's history. This shows a photo of one of the typical fractures that occurred with the steel girder pulling a divot out of the steel column. It takes a huge amount of energy to do that. And so myself got started in experimental testing from this, and lots of people. It was a coordinated effort around the country to try to understand what happened, try to prevent it from happening again. And myself and others worked on different types of connection technologies. We did figure out what happened, and people have developed a number of connections that are much better. And so a lot of these are codified through the American Institute of Steel Construction, what they call AISC 358. We call these pre-qualified connections. They've been developed and tested, and now engineers can use them without doing a lot of extra analysis and testing. And so you see some examples here. And what I started to figure out as we were developing all this is we were basically taking the damage that occurred in Northridge and moving it half a beam depth down the length of the beam. We're still going to have damage there, damage that's really difficult to repair. And we're not going to have these what can be deemed catastrophic fractures, but we're still going to have a lot of damage. And so this got me asking myself, are we really going about this correctly? The way we design buildings in this country is that hopefully in light events, they're not damaged. In moderate events, they have damage that's repairable. And in heavy events, they might be so damaged that they have to be condemned. We design buildings ideally not to collapse, except maybe in the most extreme situations, but we don't design them not to be damaged. And you can have a perfectly new building designed by a perfectly good engineer that is so damaged that the building really can't be recovered if the event is big. I think we could do better. And this is where we start to think about resilience. My colleague David Marr, West Coast engineer, calls this unsustainable engineering. Costly permanent damage, large permanent interstory drifts. So the first system we started working on about 20 years ago with Greg Deerline, Helmut Kronwinkler, Sarah Billington at Stanford, funded by the National Science Foundation and AISC, is called a controlled rocking system. And it has three components as an example of what we could be doing. The first is that you take steel brace frames that normally resist the earthquake and you put them in a trough to allow them to rock back and forth. Then you use that motion to engage what we call replaceable energy dissipating fuses. These are shown in gold, and this is supposed to be rocking back and forth. Let me see if I can get it going. Shown in gold, so these are standard steel plates with diamond-shaped cutouts. And if you make those diamond-shaped cutouts, you could shear that plate plus or minus 30 or 40% of its original dimension, and it doesn't fracture prematurely. And then the third component is in green, that's vertical post-tensioning. It snaps the brace frames back to vertical, then you could pop out the old fuses, put in the new fuses, you're ready to go again. Ideally, the brace frames stay damage-free. Rest of the primary structural system stays damage-free. This is an example of how we could build resilience into our system. We did a whole range of testing on this, but it culminated in a series of shake table tests at eDefense, the largest shake table in the known universe. It's outside Kobe, Japan. And this shows another configuration of the system in gold is a three-story brace frame. This is at 2/3 scales, about 30 feet tall. And as it shakes back and forth, sways back and forth, the white post down at the bottom center goes up and down and engages the fuse down at the bottom center. And then the post tensioning is in black on either side. The gray are linear sliders with masses. So as the shake table shakes, The sliders go back and forth and throw all the inertial force into the specimen, and the primary thing resisting all that is the fuse. So you can see a specimen getting dropped into place here. You can see a person on the right-hand photo that gives you a sense for the scale. I don't know if you can hear the sound, but this is an example of one of the shake table tests, about twice as big as Northridge. You'll see in the lower right those sliders going back and forth. On the upper half are the two corners, the base. They're going to be rocking up and down in the trough. And on the lower left is the fuse getting in action there, with the post-tensioning on either side. And in fact, this steel is so robust, in many cases, you probably don't need to replace the fuse. I wouldn't call it it's not damage-free way of resisting this, but it's certainly robust. And if you look at typical results, you could see a trace of the displacement versus time on the upper left. On the lower left is the overall load deformation, essentially. And so you could see that it's dissipating energy and then coming back to zero displacement at each cycle. And then on the lower right is the behavior of the fuse itself. Those big loops are how it dissipates the energy from the earthquake. And early adopters have been using systems like this. David Marr used this in the Orinda City, California government offices. This is the fuse is a deformable angle, like you see down at the base of this brace frame, and the post-tensioning loops underneath to give it enough length to self-center. Greg Luth used this in the USC School of Cinematic Arts here with precast concrete panels instead of steel brace frames, connected by what we call the butterfly fuses, those diamond-shaped cutouts. David Marr used this in the Hewlett-Packard Foundation headquarters with a brace frame down in a trough. The Tesla Gigafactory in the seismic zone outside Reno, Nevada, Greg Luth using this for the brace frames there. And indeed, in the 15 years or so since we completed this work, there's been a huge range of ideas and innovations around the world. In that AISC 358, there's a couple of connections now. We see on the left, these have replaceable components that are going to be the ones getting damaged. Easily replaceable components. Now, you still might have a lot of connections, but it's at least a step forward. On the right, you can have self-centering braces that absorb the energy and help the structure to self-center. You could take these ideas to other structures. Like I did some work funded by IDOT with Jim Lefebvre and Larry Fonstock on looking at standard elastomeric bridge bearings in the Midwest that are used for temperature control on bridges. We tested them to see if they could do high amplitude deformations like you would see in an earthquake, so that you can essentially isolate the superstructure of the bridge from the substructure and protect all of them. So, like to see these types of ideas propagate. That's a little bit of background. Let me tell you about a more recent project. This was done with a large team at Northeastern, funded by the National Science Foundation Critical Infrastructure Resilience Program. And we were looking at the resilience of emergency healthcare networks in urban coastal regions subjected to hurricanes. And so the team here was large. It had electrical engineers who were experts on power and communications. It had industrial engineers who were experts on the emergency healthcare system and how those processes operate. We had computer scientists who were doing agent-based modeling of people before, during, and after extreme events. And I was the civil engineer, so I was dealing with understanding the hurricane loading and how that hurricane loading damaged critical parts of the infrastructure that then would feed into these other systems. So we started looking at hurricanes, and here's a map of the hurricane tracks in the United States over many decades, a little bit of a disarming figure. And we were looking, for example, at the behavior of transmission line towers subjected to hurricanes. And indeed, the whole transmission line tower community for our utilities, the people who work with our utilities, great community, very efficient designs. They work a lot unto themselves, not a lot of work published out there. But these towers will collapse in hurricanes. And you could see it going back decades now. Hurricane Rita, for example, on the left. Much more recently, Hurricane Ida on the right. So just to dive down a little bit technical here for a couple of slides, we had to simulate these, we had to develop new beam finite elements in a program called OpenSeis that we use for structural analysis. Because electric transmission line towers are made from angles, and angles are asymmetric members. They're not singly or doubly symmetric, and so they exhibit different kinds of behavior than more symmetric members might. And so we wanted to be able to look at the combined axial flexural torsional behavior of these, and in particular what's called flexural torsional buckling, which is a manner in which these can buckle that's fairly distinctive to a cross-section like an angle. And so we developed geometric material nonlinear formulation to be able to simulate this. We had pretty standard cyclic stress strain and what's called a fiber formulation to handle the material nonlinearity. We validated against some buckling theories that were put forward by Kitty Pornchai. You can see the plots on the left is elastic buckling of these angles. On the right is inelastic buckling. We're able to match those results quite well. And then we use that to build out models of transmission line towers and analyze them subjected to hurricanes. And consistently now for years, we've been looking in the literature, and unless I'm mistaken, I don't think anybody's actually done full nonlinear time history analyses of transmission line towers subjected to hurricanes. If anybody knows, anybody who has, I would be interested, because we haven't found anything out there, which is a little surprising because we've done a lot of this in earthquake engineering. But earthquakes take a minute. These take days. And so there's a computational issue here that's real. So what we did is the other challenge here is that hurricane measurements out in the field on the loading often are done every 6 hours, once every 6 hours. If you get high resolution, it's once every hour. And so it's much tougher to really understand the variation in the wind loading as compared to what I was used to in earthquakes. So what we did here is came up with an approach for getting 10-minute wind speed and wind direction intervals. And then we skipped the beginning part of the hurricane, ramped it up quickly like you see in the blue line on the left, and then ramped it down at the end, but analyzed many hours of the core of the hurricane. And if you see in that blue graph on wind speed, when it dips in the middle, that's when the eye of the storm is passing near your structure. And then in brown shows the change in wind direction that goes with that. Once you have those mean wind speeds, we use what's called a Caumal spectrum to give us the dynamic fluctuation within each 10-minute interval. And if you put all that together, now you have your dynamic hurricane loading at different heights along the structure. And so we use loading like this to analyze transmission line towers like we see on the right. And so we did these analyses. You could see the results on the right, the loading on the top, and then, for example, the two translation and vertical displacements at the top of the transmission line tower on the lower right. And these analyses are picking up the full material nonlinearity, buckling of the members, and so on, so we could start to track damage in these transmission line towers in detail. And once you have that, then you could start quantifying and characterizing the damage. And you could look at any limit states you want, first yield of any of the members, all the way up through potential collapse of the structure. And we did this through using what's called incremental dynamic analysis, which is a concept that was developed for earthquake engineering. We mapped it over now to hurricanes. And so each of the lines on this graph on the left are a single hurricane based on analyzing a single transmission line tower. And it's a plot of gust speed versus maximum displacement of the transmission line tower during the hurricane. And so what you do here to form each of these lines is you take a standard hurricane and you cut the amplitude by 90%. So you do 10% of the amplitude. You do a whole analysis, take the max displacement, that forms 1 point on the curve. Then you do 20% of that hurricane peak amplitude. Do a whole analysis, that forms the second point of the curve. And then you keep increasing it until you go up to 200, 300, 400% of the amplitude of that hurricane, and that gives you one curve. Then the different lines are different hurricanes, so we start to get a stochastic sweep of what might occur in the loading. And then from there, you can plot what the damage is at different gust speeds. And so the red points are our estimation of when collapse is going to occur. Once you have that, you could start forming what's called a fragility curve, which we see on the right, This is a quick estimation of how much damage, or the likelihood of damage, of collapse in this case, of your transmission line tower to a given wind load. And once you have that, then you could start building resilience strategies into your transmission line towers. You could try out different ideas and start to see how that probability of damage is going to occur. For example, there have been people who have proposed using viscous dampers on our transmission line towers. I'd like to look into putting replaceable energy dissipating fuses at key connections in these transmission line towers. And then we could see how the likelihood of damage or collapse occurs. And once you have that, then you could start looking at the whole power network. And so we used Massachusetts as an example because we were able to get access to the power grid. And in fact, on the lower right, you could see mostly looking at Cape Cod, National Seashore, my favorite part of Cape, so I want to really make sure that stays resilient. And so we did a whole series of analyses here and looked at different approaches and impact on regions, and in particular feeding back into the emergency healthcare network for resilience of the power grid for hurricanes. That gives an example of what we could do here. Another project funded by NSF I've done with HowSun is on integrating AI, in particular physics-informed machine learning, into the world of seismic engineering of steel structures. And so we did this in a variety of ways, and I'm only going to talk briefly about this. On the upper left, one thing we did is develop what's called an AI autoencoder that we use to select which ground motions we want to use to get a stochastic suite of ground motions for analyzing structures. And there's been a whole history of ways of selecting what those ground motions should be. We just wanted to explore using an AI autoencoder to do it. And so what an AI autoencoder does is it takes to train it, you take a bunch of ground motions or their spectra, and you put it through the autoencoder, and it creates what's called a set of latent parameters, say half a dozen latent parameters. Those latent parameters are not physical, but they essentially, through the AI, are representative of that ground motion. And then you could decode it to reform the ground motion so you can validate that you're doing this correctly. And once you've put a bunch of ground motions through there, you get a whole set of latent parameters. And then you can cluster those based on their values into the clusters like we see in those colored points there. And they naturally divide themselves up into clusters. And then if you select one from each of those clusters, you've got your set of representative ground motions. That's basically what we did. Once we had those, then we started by developing what we call our ground truth. We took a series of standard steel frame structures and we subjected these to typical nonlinear structural analysis for the earthquakes like we've been doing now for many years. That's what's shown on the upper right. That gives you the response of that structure, displacements, forces to those earthquakes. That's what we're going to use to train understanding the behavior of steel structures in earthquakes. The second row then is the training of a physics-informed machine learning algorithm where we take a bunch of earthquakes in and train it based on some of the data that we just generated to be able to predict the behavior of that structure without actually running a structural analysis. Once you have that, on the right side of that second row, you could take a lot more earthquakes and run them through and get out a prediction of the response. Once you have that, you can create incremental dynamic analysis on the lower left. And so on the left is what we created just using standard structural analysis. On the right is what we generated based upon the AI. Once you have that, you could start creating fragility curves. And we're showing examples of fragility curves done with structural analysis versus fragility curves done with AI. And by the time you get to fragility curves, you've got a little bit of play in how accurate this needs to be. These are just estimations of achieving different limit states. And the bar chart on the right shows that it was about 5 times faster, which is why we're doing it. So AI's nose is under the 10. And we'll see where this goes. Now, if you want to have resilient communities, one of the things I've been working on, and I think there's a number of people here working on things like this, is use of autonomous aerial vehicles to automatically circumvent structures, automatically take laser scans and camera images And I've been working with robotics people at the Carnegie Mellon Robotics Institute and then roboticists at Northeastern to do this. Funding's from NSF. Tashkin Padir, in particular, great roboticist. And then I've been doing the civil engineering part of this, which is automatic object detection and automatic damage detection. So this set of videos shows autonomous aerial vehicle automatically circumventing a structure. That's what my roboticist friend's contribution is. Creating a laser point cloud, also camera images, a whole series of camera images, a lot of data. On the right, then, I take that data and have developed heuristic algorithms for steel bridge structures to automatically segment the bridge into sections and then detect, ideally, every object. The deck, braces, gusset plates, bolts, welds. You can use that geometry to do automatic mesh generation for finite element analysis to analyze your structure, like on the lower left. And then most of what I did was on the lower right, looking at automated damage detection. We were looking at concrete cracking, concrete crushing, steel section loss, steel rupture, bent members, et cetera. And so I hope these can be human-assisted robots that can really augment our ability to go in. We've done this for routine inspection, but also done some work after an extreme event, especially in dangerous areas. There's a lot of opportunity here. I think an increasing number of people are working in this now. And last project on resilience, it really forms, I'd say, looking at traditional structures as a basis for what we're going to do in sustainability next. This is a project called the Steel Diaphragm Innovation Initiative, finished up recently with Ben Schaefer, Matt Etherton, Sam Easterling, and Raphael Sibeli at a number of academic institutions, and Walter P. Moore, you see in the bottom there. This funding was from NSF and the steel industry, probably the largest grant from the steel industry, I think. And we did a whole lot of work over a whole lot of years. We developed prototype structures. We did complete 3D analyses. Well, let me step back and say the purpose of this was to look at the three-dimensional behavior of steel building structures in large earthquakes, and specifically to look at the behavior of the floor diaphragms, the concrete composite deck floor diaphragms that are ubiquitous, typical in steel buildings. Surprisingly little work had been done on looking at the floor diaphragms in earthquakes. And we had a variety of motivations for that. So did a whole series of analyses, did a whole series of experiments. I'll show you a culminating one. And then did topology optimization and so on. Big team working with practitioners for a number of years. So it culminated in a full-scale test that we did at Northeastern on indeterminate floor diaphragm, steel frame with concrete composite deck. This was about 28 feet wide, about 22 feet deep, about 10 feet off the ground. And in the photo on the right, you could see in black, those are actuators oriented in the plane of the floor. And so these are going to be cycling back and forth like the inertial forces from an earthquake that would throw shear into the diaphragm. And that diaphragm needs to take those forces out to the vertical seismic force resisting system like your brace frames. And so we're studying that behavior and the balance of the damage in the concrete deck versus the shear connectors that are connected to the steel beams that are expected to transfer all those force and all that force into the steel system. You could see the steel framing here. This is one of the first quasi-static tests that have really had indeterminate steel framing like this with a lot of gauges on it. There's certainly been big shake table tests on steel frame structures, but it's more difficult for them to instrument and observe the damage at the level of detail we're able to do here. So this is a time lapse, and this is standard construction like we're using ubiquitously now. Lightweight concrete, 6 1/4 inch deep deck, 3-inch metal deck. And what's happening here, you'll start to see that we're going to cycle back and forth, and we're looking again at the balance between how is the concrete getting damaged versus how are the shear connectors that connect it to the steel getting damaged. And the behavior here is as expected. You'll start to see diagonal cracking in the concrete as it absorbs the shear. And eventually, to pour this big deck, we had to do 3 concrete trucks. And so they don't all come out identical, and the weakest concrete ended up being on the right, and that's where we finally had our failure. And this shows typical results. The strength of this was very high, much above what we would normally predict for design, which is shown by the horizontal lines. And it had a lot of cycles before we failed it. This kind of test forms a basis for what I'm about to show you in some of the work ongoing. Okay, let's shift to talk a little bit about some of the work we've been doing in sustainability. And as an example of that, I want to start by showing what happens to our construction materials right now at end of life commonly. This graph's a little bit old, but it's still pretty true. On the right, you could see steel is, almost all of it is recycled. And indeed, almost 100% of structural steel for buildings, et cetera, comes from recycled material. On the left, concrete, about 75% is downcycled, and I hope we can increasingly improve that. Wood, a lot of students think, oh, if I want to be sustainable, I need to use wood. I think we need to be aware that about 60% of it's going to a landfill right now. And unless we start addressing that, that's not okay. So one example of a project is design for deconstruction, designing structures to be taken apart at the end of their useful life and having their components reused instead of recycled or scrapped. And this is a design issue. And so working with Mark Webster at SGH and my colleague Matt Eckelman, funding from NSF and AISC, we developed precast concrete planks for floor systems in buildings that are clamped to the top flange of steel buildings, steel beams in steel frame structures. And by clamping them, you can unclamp them at the end of the useful life of the building and ideally reuse these precast concrete planks. We envision this in the context of all steel construction, all bolted steel construction rather, so you can unbolt the rest of the structure, ideally refabricate, reuse these beams. You could see sort of a interlaced pattern of these planks that give one example for a floor system. My colleague Matt Eckelman did life cycle assessment on this, and it shows 4 different sustainability metrics here. And on the left is traditional construction. And then the next one is if you use design for deconstruction but don't reuse it. And you can see it's actually worse. And so we're going to need to continue to develop methods that actually make it better. But then if you start reusing it, then we start gaining some real advantages. So this is an example of the type of thinking that we're trying to do. And we first studied the behavior of the clamps by doing these push-out tests where we cycle a steel flange back and forth like in an earthquake to see how it transfers force from the plank to the steel. Had a whole series of specimens here, different bolt sizes on the clamps, different number of clamps, different reinforcement in the planks. And this shows typical cyclic results as we go back and forth. And basically what it shows is these retain their strength very well, and they can go to very large slips. In fact, essentially they're transferring the force between the steel and concrete damage-free. And so it's a whole new force transfer mechanism that I think we can consider for applications where it's appropriate. Here we're doing a full-scale beam test, composite beam test with these precast planks. You can see the clamps shooting down the length here. We did 4 different beams, different sizes, different number of clamps, ranging from what we call fully composite, lots of clamps, to partially composite, not too many clamps. And this shows some typical results. This is the total vertical load, like from gravity, and the center beam displacement that we did out at the stress lab. And so we loaded these up, we unloaded a couple times to make sure they can retain their strength and stiffness. And then you get great ductility on these, and they come in well above the design strengths in most cases. So very robust system. We think this kind of idea has potential for use. This shows all of the results compared to the design predictions, and we are looking good. So last 2 projects I want to talk about are new, and so just very briefly. The first is called Fast Floor, and it's with Ben Schaefer, Matt Etherton, Oner Afshi, Sam Easterling, Ron Klemenczyk, Purdue grad, Josh Morass. And we're looking here at an all-steel system. This is funded by the steel industry as part of the AISC Need for Speed initiatives. It's called Fast Floor. And this is a modular steel system, 2 steel beams with a 10-foot wide plate, asymmetric, like you see on the upper left there. And these modules are going to get dropped into place, and they are going to be very quick to construct. And we're doing vibration testing like we see on the left here. I'm going to be doing beam testing like I showed you for the design for deconstruction like you see on the lower right. This is a video from Clark Construction. And on the left is fast floor, dropping these modules into place. On the right is typical construction. And so in typical construction, you can see they're putting in the steel framing now. You can see fast floor on the left. And they're still putting in the steel framing now. You can see fast floor on the left. Now they're starting to put in the metal deck, and you can see fast floor on the left. And yep, we're still putting in metal deck on the right, and you can see fast floor on the left. We're still putting in metal deck on the right. We haven't even cast the concrete yet. And we're done on the left. Now we're starting to get the concrete poured. So you get the idea. In addition, the steel industry is one of the biggest users of electricity in the country, certainly. And they are working with the utilities to go 100% green energy, 100% recycled material, 100% green energy. I'm talking to AISC about advocating for electric trains, electric trucks, electric cranes, and now we're getting somewhere. The steel industry is doing a great job at using renewable energy in what they call the EAF's electric arc furnaces, and that's the vast majority of steel for the construction industry. But we still have a long way to go. This complicated graph shows that about 2/3 of the material is coming from iron ore still in the world, about 1/3 from recycled material. And indeed, the United States is not exactly the issue. China produces more steel than anybody else and more emissions. If you want to be a civil engineer, and you're going to need to be thinking globally, like the first slide, if you really want to make a change. So how do we interact with these other countries and try to help them along? The next project, funded by DOE with a big team, is looking at using cross-laminated timber floor diaphragms in steel frame structures. And we're using the CLT to sequester carbon as a way of being more sustainable. We're looking at new types of cross-laminated timber using what's called low-value species. So these are East Coast trees. The West Coast likes to call themselves high-value species. We have been designated low-value species. I assume that's not politics, but we'll see. And we're developing this for design for deconstruction by having through-bolt connectors where you could work just from the top to bolt these down. And we'll be doing a whole set of tests like the beam tests, diaphragm tests, like I was showing you. Just a few thoughts to wrap up here. You've all probably heard of LEED. LEED is an approach for addressing sustainability in buildings. It's kind of a point system, and I'm not quite sure LEED is doing everything we'd like, but it's a start, and I would say everybody kind of knows about LEED. The general public knows about LEED, the owners know about LEED. U.S. Resiliency Council has been trying to do the same thing on resilience, where they have a silver, gold, platinum rating system. And these types of things are important to shift an entire culture, which I think is what we need to do, so that unlike Superstorm Sandy, where we had an island of resilience planning in a sea of darkness, we could start to do better. A few years ago, I was working on topology optimization with one of my postdocs. And topology optimization is when you take a mass, like a mass of a structure, and the optimization algorithm shows you where to orient all the materials to be able to resist the wind loads well, for example. And these create very organic forms. And Bill Baker at SOM takes ideas like this and turns them into practice, like 80 Fulton Street in Chicago. I've started to put all this together, and I ask myself, can we optimize structures through having sustainability and resilience goals and metrics as our premier design objectives? I think I'd like to help shift the whole culture so that sustainability and resilience are our premier design objectives, underpinned by strength, stability, serviceability, economy, and aesthetics like we do now. And in fact, thinking about the regional modeling, I'd like to think about topology optimization of whole regions. This is showing Memphis, Tennessee, with sustainability and resilience as our premier design objectives. Can we take our topology optimization ideas, working with our systems people in civil engineering, like in transportation and so on, and start to look at this. As president of SCI, I've been able to work with other presidents of other organizations around the world. That's been a real privilege, including Tanya de Hoog, current president of iStructE out of the UK, who gave her inaugural address on the date you see here. You can look it up on YouTube, and I encourage you to listen to it. And she is talking about 3 action steps to address sustainability: advance technical innovation, achieve lifelong learning, and act together. And these are things that we can do to start to shift a culture. You know, I've worked with architects for a long time, and they might say to an owner, "Oh, we should do this, it's going to be beautiful." And the owner says, "Oh yeah, that's a good idea." If they say, "Oh, we should do this, it's going to be sustainable," the calculator comes out and they start calculating cost. This is going to require a culture shift. A culture shift so that the public and the owners thinks if it's not resilient, it feels unsafe. If it's not sustainable, it feels ugly. I don't even want to look at it. Or let's end on a positive note. If it's resilient, it feels safe. If it's sustainable, it feels beautiful. Thank you very much.
We have time for questions. We have a mic that we can go. Questions, please.
Hi. I'm a freshman here, and I just sort of stumbled into here, and I was really inspired by what you saw, cities and the designs of cities. Have been a big passion of mine since I was little. What would you recommend for, younger people trying to get into the field and learn about all of this?
You said you're a first-year
Yes.
engineer? Yeah. Are you a civil and environmental or civil engineering major? Or?
Perspective, it's like first year. Everyone
Right,
does the
fair
same.
enough. Okay, I think it's a great time to be an engineer, so that's a good decision. And lots of different ways to get into this. But perhaps a straightforward way is start to learn about the faculty in various fields. If you want to learn about the faculty in civil engineering, talk to GS. And he could point you to different faculty, and you could start doing research right now. I have a bunch of first-year students doing research with me. They do all sorts of things. They make flyers about our projects. They do literature reviews. They help make websites. And then from there, you could start doing more sophisticated research. So that's one pretty direct way to do it. You could also think very holistically about your education. I'm a big proponent of the liberal arts because it plays right into civil engineering. If you want to think about working with communities, there's all sorts of courses out there. You could take public policy courses. You could take architecture courses. You could take computer science courses. We can call computer science liberal arts. You can, all sorts of things that really can help directly.
Thank you.
Thanks. Hi, my name is Xiao Han, a PhD student at Environmental Ecology Engineering at Purdue.
Yeah.
So I'm not a civil engineer, so I want to ask a more sustainable question. You're talking about you are replacing the concrete building with steel. Steel building could build faster than concrete building, and steel is more sustainable, lower carbon footprint because you use 100% renewable energy. So I'm wondering, like from a construction perspective, how many concrete buildings can we replace with steel?
Yeah.
Like what is the potential market?
Yeah.
Thanks.
So how many concrete buildings can we replace with steel? The American Institute of Steel Construction would love for me to get a question like that. I mean, my first thing is we need to float all boats here. So I personally hope our concrete friends are developing really green solutions. I know there's some work here going on that. I hope my friends in timber, masonry, polymers, everybody needs to be working on this. So I don't necessarily see it as replacing concrete, although concrete floors, maybe. That's obviously what we're trying to do here. Concrete is a ubiquitous material out there in the world. This is a big issue. So I'm not going to answer your question directly. I think I'd rather work on all of these together. But I will say this, in our cross-laminated timber system, it's much lighter than concrete. So that decreases our foundation systems. It's decreasing the size of the steel members. I mean, we're just using less material in general by having a much lighter floor. And but it's all integrated. You know, what is that going to mean for high seismic zones and so on? Yeah, these are really challenging engineering design issues.
Thank you.
Yeah.
Hi, I'm Sydney. I'm a first-year master's student here. So obviously, from what I've known and experienced, is the construction industry generally is very slow to adopt to change.
Yeah.
So you mentioned needing a culture shift in the
Yes.
industry as an entire entity. How
Yes.
do you plan on going about that? Because I feel like a lot of the, obviously now it's follow the money, follow
Yep.
everything else, and
Yep.
that's outside of the engineering industry and more in the
Yep.
technical side of things.
Yeah, that's a great question. So I'd say there's a few trends going on, and we need to harness the trends. First, an increasing number of engineers. If we could think about public policy, that's a good thing. And for example, I led a workshop through the Structural Engineering Institute at Northeastern this summer called Toward Zero Carbon. And it was an interdisciplinary group that was brainstorming how to go toward zero carbon in the built environment. And we had there the Assistant Secretary of Defense in charge of infrastructure and environment, basically, who was responsible for 500,000 buildings. And we had there the head of infrastructure at the General Services Administration in the federal government, who's in charge of lots of buildings, not quite 500,000. And those two stood right up front and said, we want to be pioneers on this. And if those two individuals set policy in those two organizations, the entire industry is going to shift. And so public policy is big. And that can, if they require it, the designers are going to adjust. The contractors are going to adjust. That's the first trend. The second is there's an increasing amount of innovation happening in our world, and the contractors are not ignorant of this, many of them. You have great contractors that interact with this firm, this department rather, and this college. And I'm sure they're aware of this, and they're struggling. An increasing number of graduates coming out are going to those places and saying, we want to talk about sustainability. They are recognizing the power of AI, for example, for construction estimating and so on. And I say, can we take AI and talk about sustainability and resilience? They see new materials coming. They see some of their competitors becoming innovative. I mean, there's innovative products that are being developed that they're increasingly integrating into their practice. I think we could do a lot of this revenue neutral. This stuff is not necessarily more expensive. That's an engineering issue. So I think it's happening. And whether it happens fast enough to achieve those 2050 goals, or whether the planet is just going to self-correct while we all scramble around, I'm not really sure. But, you know, you got to give it the try.
Thank you, sir.
Hello, my name is Anish. I'm a first-year PhD student. I was wondering if you could talk a bit more about, like, have you done, like, any seismic performance tests on the timber laminated structure? And also, what does fireproofing for that type of system look like?
Yeah. So have I done any seismic tests on the timber structure? The answer is not yet because the project's new, but it is for high seismic zones. And by the end of the project, I hope to. I plan to, and therefore I hope to. And depends how fast the PhD student works, by the way. Yeah. And then with respect to fire, vibrations, acoustics, all issues. Our team is looking at some of these, and then the Department of Energy has funded other teams to look at others. And in particular, our friends at Oregon State, much more adept at the fire issues. So I am in communication with them. Plus, we have practitioners on the team who are much more adept with fire. So they're keeping an eye about whether our solutions can be addressed for fire. But I'm not an expert in fire. Yeah.
Do we have time for one more? It's 2 on the nose. It's up to you. One more question? He has a question. You had a question.
Last question.
Are we negotiating?
Hello, I'm a PhD student as well. You shared details about a lot of projects, and all of them are fantastic. But if you were to pick one based on, which one do you think has the highest potential out of all of them?
Oh, boy. Choosing between my children. Can I say all of them? Yeah. I'm really, okay, here's an idea I didn't quite present, which is if you look at the last 2 projects, Fast Floor and the CLT project, what I'd like to do is those projects designed for deconstruction, but also incorporating the fuses, which we're thinking about. I don't know if we'll quite get there. And if we could incorporate the fuses so that we isolate the floor diaphragm from the seismic force resisting system. Through the inertial force of the diaphragm, we engage those fuses and basically protect the seismic force resisting systems in some ways. It'll be transformative for the building industry. I'd like to do that. Yeah.
All right. Thank you all very much. Please give Jerry another round of applause.
Yeah. Thank you very much.